Okay, everyone, we good to go? Now, before I start this particular idea, let's just get some context for where we are in this topic, okay? Areas under curves. We started with this whole idea of how do we get shapes, right? Like this, and they don't fit all of the normal kinds of shapes that we know how to, get formulas from and all that kind of thing. So how do we get an area? And we've looked at all these different ways of doing it. We looked at the exact way, which we've called integration, right? We've looked at a couple of not exact ways, approximate ways. What were they? Number one, trapezoidal. Number two, Simpson's rule. Okay. Trapezoid. Oh, by the way, yeah. So, did I tell you this? Did I tell you about why it's called Simpson's rule? Did I tell you? I can't remember. So the first, it's really tricky finding, attributing stuff in maths because it's not like, people don't invent stuff in maths. You discover something. Like there's a relationship, it always exists there. And we tend to name it after the first person who recognized it, right? Or if it's got some other appropriate name, we don't call them Riemanns. We call them Riemanns. But anyway. So the first person we know about who used the Simpson's rule, which was put a parabola through it, right? Was actually Kepler. Who was Kepler? Do you remember? He was a scientist. He was a space guy. He's an astronomer. Why isn't it called Kepler's rule? Because Kepler was German. And it's not that we don't like Germans, it's just that English, he's not alive anymore.
Because they're Alsatians and
they just didn't know about it.
Germans.
They just didn't know. Simpson was British, so anyway. Hey Richard, grab some.
Getting lost.
Okay, now, we looked at those methods of approximation, then we saw that you could use integration not just to work out areas. What else could you work out? Volumes. Specifically, what kind of volumes were we looking at?
Solids of revolution.
Yeah, that's right. You turn around, you get the idea. Okay, now at this point, we've learnt, I think, all of the theory you need for this topic, okay? So all I'm going after now is some of the trickier kinds of concepts, the side ideas, which you might meet a question, and having not had it explicitly explained to you, you might be like, I don't know how to do this at all. And it's a trick that you could do yourself, honestly, but I'm just going to try and save you some time. Okay. Now, when you see the word evaluating, okay, that should give you a clue. What kind of integrals are we talking about? There's only two. Which kind am I talking about if I'm saying evaluate? I'm talking about definite integrals, okay? So I'm going to give you a definite integral, right? And I want you to stare at it for a little while. If you can see how to work it out, then that's great. Keep it to yourself for a second, right? But for the rest of us, let's try and work out what this is equal to. Hold on. No, wrong number. Try that next time. Let's go to this of this. Okay. So you look at this question, and hopefully you scratch your head for a second, because what kinds of functions do we know how to integrate? Well, we know how to integrate just regular old sort of polynomials, right? So if I had said x squared dx, no problem. Power up, divide by the power, all fine, okay? We know how to do stuff like, say, if I gave you this, you'd still be fine. What would you do to that, by the way? What would be your first step?
Substitution.
You could go, let u equal, and then you would choose something. Now, I wonder, if you've done enough exercises of substitution, you start to get used to, it gets quite predictable, right? So some of you might be at the point where you can say, look, I don't need to do any substitutions here. I'm just going to do this. Why would I do that?
Because it's the derivative of bottom
Yes.
function, therefore it's 1 power.
So now this is in the form f dash on f. So you'd go straight here. Okay, so we're getting there. This comes in practice, okay? If you couldn't see that immediately, no problems. You would go let u equal, and you would do the full thing. Okay. Now, we've got a few other kinds of families, but this is not one of them. I told you that the integration of log x is possible if/when you learn integration by parts. But I'm telling you in advance, by the fact that I've given you this question, you should know how to do a question like this. Okay. Now, remember, I've given you this heading, right? Evaluating indirectly, okay? So the direct way would be, okay, think about what kind of primitive function this came from, right? And then that'd be capital F. You go f of b minus f of a. That's the direct path for a definite integral, right? But there's another way. There's a less direct way. Okay. What is a definite integral about? What does it mean? Where did this topic start?
Area.
It started at area. Right now, help me out. What does this area that corresponds to this definite integral, what does it look like? Okay. So draw yourself up a set of axes. Now log x. What does log x look like? How would you describe it?
Looks like that.
It looks like that. Okay, so it starts nice and close to the y-axis, right? It's climbing, but then it slows down, and it slows down forever. Okay, so it gets slower and slower and slower, but it does keep growing. It doesn't approach. There's no limit. There's no asymptote. Nothing like that. Okay. Now we've got some. We've got one intercept here, right? What's the intercept? It's 1. Okay, so log of 1 is 0. Yeah, thank you. Okay, I've also got an asymptote here, though it turns out that for this definite integral, I'm not that interested. Okay, 1 happens to be my lower boundary. Okay, which is interesting. E squared, what's E roughly? 2.7. So E squared's somewhere between 8 and 9, I guess. Okay, so my scale's pretty awful. Hopefully yours is a little more accurate, but just for the sake of illustration, I'm going to pop E squared there. Okay, make yours a little better than mine. Well,
E
this
squared is 7.389.
is it really? It's less than 8. Oh yeah, yeah. Okay, I guess it's low enough. Okay, sure.
That's E squared. I thought it was E.
E squared.
That's
Yeah,
why
no, it's not
accurate.
close to. Yeah,
If it was
sure.
E, it would
It is
be
close to E,
less.
not close to E squared. But anyway, I'm just using this for illustration, right? So I've got an area underneath the curve. Okay? So far, so good. Now, this is sort of helpful. At least I got a picture in my head. But now I come back to my original question, which is, how do I work out such an area? Okay? Now, don't actually say it, but, and I know I've told some of you this already because you've asked me similar questions, but can any of you, without saying it, see anything that might be useful to us here? Anyone? You think you see something? Got an idea? Okay.
It's definitely a triangle.
Why don't you shoot? Why don't you shoot? Just and it's I hope. By the way, this is really hard. Number 1, it's a selective school thing. Number 2, it's an Asian thing. We hate being wrong because it's like I don't like being told that I'm wrong. I personally don't like being told that I'm wrong. But being wrong is a crucial part of the process of maths, science, any field of inquiry, right? Because if you can never get stuff wrong, you're never going to make any progress in terms of like, I don't know what it is equal to, okay? So if we got some validations, Clem, do you want to start?
Like the area is going to be equal to if you go from y to x.
Ah, okay. Right, well, so much for making some errors. Okay, now, can you see what he's, if you didn't catch what he's talking about, okay? This is y equals log x. Okay? Now, it turns out that, like I said, integrating log x is hard. Okay? It's possible, but hard. However, log x is very much like another function you know, which is actually super easy to integrate. Namely, it's the inverse of, let me write it in long form. This is log base e of x, right? So to get its inverse, you flip it, you reflect it across the line y equals x. Okay? So the graph you're going to get, I should put it in another color. The graph you're going to get looks like so. Okay? Now it's gone through, you get the idea. Okay? Now if that's y equals e to the x, right? Where is the area that I was trying to work out? Where is its corresponding section on y equals e to the x? Well, being that if you can turn your head 45 degrees, so you're looking at it and that's vertical, okay? If you flip it directly across, right? Directly across that line, here's what you're going to get. Somewhere like this. That's the area, right? Can you see the symmetry? Yes? Now that's 1, because e to the 0 is 1. And I guess this e squared up here should go over here. Okay? Right, now, we're almost there. We're almost there. If this is e to the x, really easy to integrate, right? But if I integrate it with respect to x, I will not get this area, because that's not the x-axis, right? What area will I get? The other thing. More specifically, areas under curves, right? So I'm going to get this area underneath. But as you can see, that area is just as good. If I can work out this area, I can work out the other area by subtraction, just like we've been doing with volumes. Yeah? Okay, so let's do it then. I'm going to calculate the blue area by calculating the green area by calculating the red area. All right, so sorry, wrong way. The actual area, this integral that I want, right, is less u. That's what I want. Okay. But it's equal to this rectangle minus the red area. Is that okay? That's how I get the green area, which is actually equal to that, right? So what's the area of the rectangle? Area of a rectangle is length times, or length times breadth or width or height, or whichever one. So the height here is e squared, and the width is, now to get up to e squared, what am I going to put in? The answer is 2. Right? Yeah, this scale is terrible. Sorry, forgive me. Okay, so my rectangle is 2 times e squared. Right? That rectangle there. Now I can subtract the red area, the area underneath the curve, and I've got to write a new definite integral for that, right? What are its boundaries? 0 to 2, yeah. That way, okay, 0 to 2. The function that I'm underneath is e to the x, and I'm bounded to the x-axis. Okay. All right, we're almost there. 2e squared, minus the primitive function of e to the x is e to the x. We're still awake, that's good. From 0 to 2, okay, go ahead and evaluate. Minus e squared minus e to the 0, which is 1. Okay, so that looks to me like double negative plus 1. Okay, so there's my final answer. This was the integral I was trying to work out. Which, by the way, I don't know about you, but it looks really sus. You're like 1 to e squared and you get 1 plus e squared. What's up with that? Now I'm just going to let that rattle for a second. It just looks unusual. That's the kind of things that mathematicians look at and they think something's going on there, I should dig at it. But my point was, if you get given a definite integral and you need to evaluate it, you can do it directly if you like. Just find the primitive, chuck in the numbers, off you go. Okay? But you don't have to, because a definite integral is just a number. More specifically, it's just an area. Right? So if you can work out an area that's easier or more simple, then you might as well do it indirectly. You'll just get the same number out at the end. Okay? Now we'll see if we remember, like in not a year's time, maybe in 7 or 8 months' time, when we have some time, if you want me to teach you integration by parts, we'll come back to this, right? And we'll integrate it, and we'll pop the bounds in, and we'll make sure we verify that we come back to this, okay? But that's pretty simple. Like, we can manage that, right? A 2-unit student can manage that. So keep it in your head. We'll be doing this kind of trick a lot when we move on to inverse trig.